Welcome to Lesson 1 for Chapter 8, Pure Mathematics Year 2. This chapter is all about parametric equations, and parametric equations are vitally important, not just in mathematics, but in many other fields as well. This first lesson, we're going to look at how to convert what we're going to call parametric equations, which I will show you shortly what they actually are, into Cartesian form. Now, Cartesian form, named after René Descartes, is the more traditional coordinate system that you're used to, which is the XY plane. So parametric equations function in a slightly different way, but you can convert them back and forward into Cartesian and back into parametric. So we're going to look in some detail at that. Before we do that, please pause the video and try the warm-up questions. Okay, and let's have a look at the solutions. So in question 1, we're asked to write our function f of x, which is a quadratic, in this form. So this is in completed squared form, as you should be familiar with by now. Notice we have a restriction on the domain here. It's not all real x values, so that might come into play later. So we're going to find out what the a and b constants are as well, and they are apparently integers. So you know how to do this. If we look at the coefficient of the x term here, it's -4. We need to halve that and put it into a bracket squared. So we'll do that first. So if I just write f of x is equal to, so it's going to be x subtract 2, halving that coefficient, all squared. Okay, that's the first bit. And we'll notice, of course, if we just do a little aside, that this part here, if we expand the whole thing, we would get x squared subtract 4x with 4 added on. Now, notice that's not quite what we want. What we want is the x squared, which we've got. They match up. We've got the -4x as well. Okay, so they match up. I'll do that in green just to show you that they are indeed the same. Okay, unfortunately, we've got +4, and we don't want +4, we want +5. So in order to make these things equivalent, what I need to do here is add 1 to make that +5. So in this expression here, I need to add 1. So that's the answer. So it's x subtract 2 all squared plus 1. So we can now write down what the values of a and b are. So a is, of course, -2. It's an integer. And b is equal to 1. Okay, that shouldn't have been a major problem. That was year 1 revision. Moving on to question 2 now. We're told to complete the table of values for the function f. This is the same function we've been talking about already. With integer values of x, ignore the row labeled t. So the row labeled t will probably come into play shortly. So we're just going to focus on the x values and the f of x values here. So if I just put in the numbers, these are integers, of course. So we've got 0, 1, 2, 3, 4, and 5. Okay, and then if we find out what the f of x values are, well, we just sub in those values. So if I plug in 2, notice the function is x subtract 2 all squared. That's just going to give me 0 squared plus 1, which of course 1. Okay, then it's 3 subtract 2, which is 1. Square that is 1 plus 1 is 2. Okay, and when I plug in 5, 5 subtract 2 is, of course, 3. 3 squared is 9 plus 1 is 10. And we can do a quick check. Does this make sense? Well, yes, we can tell as a rule of thumb. I mean, it's not totally precise, but you can usually tell we have a nice line of symmetry along here. Okay, which is what you would expect, because if you have x subtract 2 here, this is a translation of the x squared graph. Okay, just considering the x subtract 2 all squared, it's the translation of the x squared graph 2 units to the right. So you would expect a line of symmetry along where x equals 2. So that appears to be correct. What we now have to do is to plot this information on the grid provided. For x is 0 to 5. So we'll do that next. Okay, so for question 2, I've just completed the graph on the screen. I've had to zoom out a little bit. So your plot should look something like this. I've tried to draw a smooth curve through the points, and we can clearly see the parabolic shape. Now for part C, it says use your graph to write down the range of f. Now I must stress from part A, question 1, which was, or well, question 1, I should say, what was provided was a domain. Okay, so the domain for f, which I'll just write down here because it's not on screen right now and it is really important. We're taking x values between 0 and 5 inclusive. Okay, so that means that we have a restriction. So rather than considering a range as being on a real line, for example, we've got to restrict the domain to what we see on the screen right now in that plot. So let's do this really carefully. Obviously, if this was all real numbers, you can see that the range would be anything greater than 1, this value here, because this, of course, is the lowest value that y can take. But if we look at the range on screen, we're going from 1 up to 5, but it's still valid up to the y value 10. Okay, it's as if you shone a light from the right-hand side onto the graph, it would cast a shadow between the values 1 and 10, including both of them. So that's really important. The domain matters, as I've said before many times. So the range, consequently, is going to be all y values from 1 up to and including 10 because of that restriction. Now, moving on to question 3, we're going to complete the table. Again, we're going to go back to the row T, so I'll do that, and then we're going to state the range of values of T. Okay, now you can see from question 3, we're given T defined as x subtract 2, as you can see here. So I'm just going to cross-reference this with the table. Now, if we want to find T values, and you'll see the utility of this later on in this row, we simply take the x value and subtract 2 from it. So I'll just write those in. So it's going to be obviously 0 subtract 2, which is -2. Okay, and then just subtract 2 all along the way. So that's going to be -1, 0, 1, 2, and 3. So it's a sequence again, a linear sequence. And we can obviously see now that there is a range of values of T. So T is running from the values from -2 up to and including 3. So we can just write that down. Let's try that again. So just like the x and the y values, T defined using x also will have a range. Okay, and notice that the range is 2 less than the range of the x values because that's how T was defined. So 2 less than 0 and 2 less than 5. All right, so that's question 3 complete. Now we're going to move on to question 4 just to bring the warm-up to a conclusion. Okay, now going back to the original statement for f of x, I've just written it out again, more for my reference because it's not on the screen right now. And I've also written out the equation for t, or given in terms of x, which you can see here. So what we're asked to do is find functions for both x and y in terms of t. Now, simple rearrangement will get us there. If we look at the one I've just highlighted, if we call this equation 1 here, all I have to do is to find a function of x, I simply have to make x the subject. So, and that's a one-step process. So to make x the subject, we can clearly see that in 1, just by rearranging, adding 2 to both sides, x would simply be equal to t plus 2. Okay, just simply by adding 2 to both sides. So that was fairly straightforward. But now, thinking about simultaneous equations, because we have two equations expressed in terms of x. So if I call this second one equation 2, I can now replace all the x values in equation 2 with t plus 2. Okay, so I'm just going to write that down. So now sub in 2. Okay, so we'll do that next. So wherever I see an x value, I can write that in terms of t now, which is good. So we're going to have y is going to equal, now instead of x squared, this is going to be t plus 2. I'll write that in now. So t plus 2 all squared. Subtract 4 lots of x again, which is of course t plus 2. Okay, we'll just close that, and then we have to add 5. Okay, so now we've got it purely in terms of t. I mean, I could leave it like that, but it'd be a good idea now to expand and simplify, then collect like terms. So this is going to be t squared plus 4t plus 4. Okay, that's expanding the squared bracket. Then expanding the linear bracket, that's going to be subtract 4t, subtract 8, plus 5. Okay, now we've got the t squared term. Nothing else to collect with that, so it's going to be t squared. And you'll notice, of course, there is some cancellation here. We've got plus 4t right here. It's going to cancel with negative 4t, so that's gone. And then looking at the constant terms here, we've also got plus 4 to combine with plus 5, so that would be plus 9, and then subtract 8, which would give us plus 1. So that's what's left. So we're going to have t squared plus 1. So we now have an expression for y purely in terms of t as required. And that concludes the warm-up. So this is our introduction to parametric equations. There's a paragraph just explaining the principle behind it. And you'll see that what we've just done in the warm-up is the reverse process. And we're going to apply what we did in the warm-up, that knowledge, reverse it, and then we can deal with parametric equations. So let's just have a read through this first paragraph. So it says, so far we have been working with Cartesian equations. So as I've stated already, Cartesian is equations dealing purely in terms of x and y, although you can call them call the variables different names, but more generally speaking, the xy plane. Okay, these give a direct relationship between two variables, usually denoted as x and y. Yeah, which is what I've just stated. Okay, equations such as y equals 2x plus 1, y equals sine x plus cos x, and x squared plus y squared equals 1 are Cartesian equations, purely because they contain the two variables x and y. We have already shown that we can introduce a third variable. Okay, usually t, which we saw in the warm-up, or theta. Okay, but you can call it whatever you like. This variable is called a parameter. All right, and we can define equations of curves. This is the key thing here. Define equations of curves in the two-dimensional xy plane. Okay, and remember this coordinate system, this xy coordinate system, is a perpendicular system, or what we call sometimes more generally an orthogonal system, where x runs perpendicular to y. Okay, so it produces a grid. So this third variable is used to define our x and our y. And you'll see how useful they are. Then we can now talk about curves that we couldn't talk about previously. Okay, and also curves that are very, very difficult to define just in terms of x and y. So the first example hopefully is familiar to you. This is what we looked at in the warm-up. now we've got parametric equations. So these are the parameters. X is defined using the parameter t, okay, as t plus 2, and y, which I'll do in green, okay, so y is t squared plus 1, which we derived in question 4 of the warm-up. What's also specified with your parameters is the range of values of your parameter. Now you'll notice the parameter is defined between -2 and 3 inclusive. So we're only allowed to substitute in values of t between those values. And what this will do, this will generate some kind of curve that we can plot in Cartesian form. And that's our first task. Okay, we've got to plot or find an equation of the curve in Cartesian form, y equals f of x. So we'll look at that in a second. What I just want to remind you of is from the warm-up, we also discovered 2 more pieces of information. We got that t was bounded between -2 and 3, but that was based on the fact that we already knew that x was between 0 and 5, and we also discovered that the range of values of y was between 1 and 10. This is purely from the warm-up, so if you've not seen that part, please just go and have a look at that or reread the notes. Now, we're going to have a look at how to find out these 2 pieces of information from the information we've got in this example, okay? How do we get the domain and the range, essentially, okay, from this information? We're going to look at that in part B. So first of all, let's have a look at the Cartesian equation. Well, because we've got 2 equations, it's quite natural, of course, to call the first one equation 1 and the second one equation 2. I mean, you don't have to do this, but it's a natural thing to do. And what we can do, if we look at the more simple equation where we don't have something complicated happening to our parameter t, such as squaring or square rooting or something like that, just look at the equation which looks the most basic, okay, which is clearly equation 1 in this case. And let's make t the subject. So that's our first step. So we're going to, for part A, we're going to make t the subject first of all. Now, this doesn't always work, okay? We're going to look at different ways of doing this, but as a good starting point, make your parameter the subject in one of the equations. So, and I would suggest you write this down for your notes as a point of reference for your revision. So that's quite simple, isn't it? So if we make t the subject, we simply have to subtract 2 from both sides, the exact opposite of what we did in question 4. So therefore, if x is equal to t plus 2, then we just subtract 2 from both sides. So x subtract 2 must be equal to, let's do that again, must be equal to t. Okay, now we've got that, we can now substitute this rearranged form where t is the subject into equation 2. So let's make a note of that. So now sub in equation 2. And obviously what I'm subbing in is what we've just discovered right here, this bit. So we're going to put that into equation 2. So I'm just going to move over to the right-hand side, just so I've got a bit more space here. You'll have a bit more space on your page. So subbing that into equation 2, well, equation 2 is y is equal to t squared plus 1. So I need to replace my t squared with x subtract 2 all squared. Okay, and then I've got to add the 1 on the end. Now notice when I do that, I get the completed squared form immediately, which was what we saw in question 1. I can now expand that if necessary. So this is going to be x squared subtract 4x plus 4 plus the extra 1 which is obviously going to be x squared, subtract 4x plus 5. So we have the Cartesian form. Y equals f of x, so y equals all that. Okay, so that's good. So that's part A done. It's literally that simple. It's basically just substitution. Now for part B, it says state the domain and the range of f of x. Well, I could just say, well, here they are. I've written them out already, but we're not going to do that. We're going to look at how to find the domain and range purely from what's presented in front of us. Well, if we look at the two parameters, the two parametric equations, we can see that x is defined as t plus 2. Okay, now that's obviously a linear expression, which means that there's not going to be any maxima or minima to worry about in between. It's just going to be either a case of increasing or decreasing. So if the x values are purely t plus 2, then if my range of values of t run from -2 up to 3, I simply have to add 2 to all of that. So I think that's pretty simple. Hopefully that makes sense. So for the domain, this is for part B, of course. So for the domain, we've got x would simply be, I'll just define it actually. Sorry, start with the t. So -2 t up to 3. Now, if I add 2 to everything, so this is going to give me 0. Just make that in red just to distinguish it. Now, that's going to be t plus 2. And remember what I've just said, I'm purely able to do this because it's an increasing function in a sense, this parametric equation. Add 2 to that. So t plus 2 is, of course, x. So I can now write, therefore, 0, which is the lower limit, up to 5, which is the upper limit, which also corresponds with what we discovered earlier in the warm-up. Now then, that's the domain, okay? Hopefully pretty simple. Now for the range, a good idea, if you don't have that information at hand, is to make a sketch of your y parameter, okay, your y equation, okay, in Cartesian form. All right, so now you can do that if you've got the Cartesian form, and then you can just read off what the range is from your sketch. Alternatively, because we're dealing with parametric equations, we've got this form of y right here, which I'm just going to draw your attention to. So we have t squared plus 1. So we could actually sketch y as a function of t instead. Now, if we do that, that's a really simple sketch. So it's just one transformation only. So let's put that as the t-axis. Let's put that as the y-axis. So it's simply t squared plus 1. So it's going to look like this, essentially. Now, this is where we have to be a little bit careful. The t variable is only defined between -2 and 3. Okay, so just to make it a little bit more realistic, I'm just going to take a bit off this, or redraw it, in fact. So it's probably going to be more like that. And that's running from -2 up to 3. And clearly, we have a minimum value at 1, okay, which is the y-intercept in this case. Right, now for the range, we could look at what would the shadow be if we shone a light from either side of this function. What shadow would it cast on the y-axis? Well, it's going to have a minimum point at 1. Clearly, it's defined up to this point here, but obviously it's also going to go further up to correspond with this point over there. So we need to find out what those y values are. Well, if you put -2 in for t equals -2, we're going to get -2 squared, which is of course 4, plus 1, which is 5. So this y value is going to be at 5, okay, on the y-axis there. And if we put 3 in, we have 3 squared plus 1, which is, of course, 10. So this value, so I'm just going to read off, obviously this is not to scale, is 10. So we can now see clearly that y is bounded between 1 and 10, which is exactly what we saw in the warm-up, which I've already written down here. Okay, so a sketch would be useful simply because this is a quadratic, and quadratics, to catch you out, would have maybe a minimum or a maximum within the range of values of t. So you've got to be aware of that. So let's now just write down what the range is. So the range for y is simply deduced from the parametric form between 1 and 10. Okay, and you can just sort of see the sketch that I've done there. All right, so I hope that makes some kind of sense. Obviously, we're bringing in aspects from all over the course here, but you'll find perhaps in your other courses that parametric equations are really crucial, and they help you to describe a lot more functions than would normally be available to you. So now we're going to move on to some more examples. Now, before we actually move on to the examples, I just want to pause and just look at some general ideas to do with parametric curves. So the first 2 bullet points, generally speaking, a curve y equals f of x is a function, but it can also be defined parametrically with equations x equals pt and y equals qt. Now, p is just a function of t, as is q. They're different functions, and an example we've just looked at, which I'll just make a note of, we saw x was equal to t subtract 2. Okay, and then we also had y is equal to, or t plus 2, I should say, and y is equal to t squared plus 1. Now, those were examples that we've just seen, and you can tell that x is a function of t and y is also a function of t. Okay, and they don't have to be the same functions, of course. Now then, each value of the parameter t within the given domain of t. So remember, we were given a specific domain of t, which was between -2 and 3. And that's just as an example. It doesn't have to be that. It could be all real numbers. It could be positive real values, whatever. Okay, but there is a given domain of t. This defines a point on the curve with coordinates pt and qt. Okay, so that means that the xy plane can be determined using your t parameters, and you can see it more clearly in this kind of this triangular diagram, this flow chart, essentially. So we start off with some parameter t, and you can call it something else. From that parameter, we can generate an x value. Okay, and from that x value, we can also generate a y value. Now, what is not indicated on here is that to connect x and y, you would have a function y equals f of x, which would get you directly from your x variable to your y variable. All right, but they can also be expressed as a parameter t as well, as you've just seen. What's interesting about the parameter is that you can take, you can use t as your starting point, your parameter, and you can make a beeline for the y variable directly, because y will also be expressed in terms of t. So it's just a neat picture explaining what's going on. T has a range of values, all right, and we've already seen that with this example here. You're given a specific range of values, and from that range of values, you can define what is going to be the range of x. Okay, now the range of x And this is where it gets a little bit confusing. We'll see on these bullet points. So I'm just going to write an extra sentence. This is the range of x. But remember, of course, that y is a function of x, as you can see here. Okay, so the range of x is known as the domain of f. These are identical statements. So the domain of f of x is also the range of x, if that makes sense. But the range of x is also the range of pt, so some function of t. So I just want you to be clear about that. Because t has a range, that creates a range of values of x. But if x is used in a function f to create y values, that is called the domain of f. Now, the second point here, we have the range of f of x here is the range of qt, because we've defined y as equal to qt. Now, this also can be defined as the range of f of x. Okay? Or actually already states that, doesn't it? My mistake. The range of y. My apologies. Okay, so all those three things mean exactly the same thing. So this is the range of y. Right. Lastly, parametric equations can be used for a complicated curve, and I've mentioned that already, which doesn't have a simple Cartesian equation. It is not always possible to find a Cartesian equation defined parametrically. That's really important, okay? It's not a solution to everything. It's not the answer to everything. It's just another method that allows us access to more complicated curves. Okay, so let's move on to some more examples. Right, so these are the worked examples. The first one, we have a curve defined by parametric equations as shown. And these parametric equations are x equals 2t plus 1 right here, and y is equal to t squared subtract 1. So we have another linear and another quadratic equation. Notice, of course, the really important part on the right-hand side is that we have a range of values of t from -2 up to and including 5. And our first job is to find a Cartesian equation of the curve. Well, as is standard, we know we're going to be dealing simultaneously with equations 1 and 2, which I'm labeling now. So we know the drill already. We need to make t the subject in equation 1. So that's what I'm going to do first. So make t the subject in equation 1. And to do that, we have to subtract 1 and divide by 2. So therefore, x subtract 1 is equal to 2t. Divide by 2, so x subtract 1 divided by 2 is equal to t. Okay, and now we can sub that into equation 2. All right, and if we do that, let's see what we get. So therefore, we get y would be equal to, now it's t squared, so it's going to be whatever my t is squared, subtract 1. And we know from the previous step, t is equal to x subtract 1 all over 2. Now, that is a Cartesian equation. You can leave it like that if you want to. If it's if it's not asking you to write it in a particular way, you can leave it as it is. Now, in a sense, it is asking you to write it in a particular way because it says y is equal to f of x. So what that means is that y has to be the subject of your equation, but that's no problem. Y is definitely the subject of the equation, but whether you expand the right-hand side of this right here, that's completely up to you. Okay, plus there's a lot of information locked in completed squared form, which I'm going to tap into shortly. So for part B, we're asked to state the domain and range of f of x. And as I was kind of blathering on a bit earlier about this domain and range business, I'm going to show you what I mean by sketching the domain and range using graphs. So for the domain, we're going to use this space up here. So for part B, the domain, we can sort of sketch what the domain might be by sketching the function x equals 2t plus 1. So if I just draw that, and remember t is valid between -2 and 5. So this will be the t-axis, and this will be the x-axis. And we know it's a straight line graph. So, and it's quite steep and it crosses at 1. So it's going to be something like that. So this is the graph x is equal to 2t plus 1. And obviously this is not to scale. I'm just using this as an illustration. So if you're looking at t values between -2, now if we just think about where this graph crosses the t-axis, which is right here, that's going to be at -1/2. So -2 will be somewhere over here. I'll just put it in here. And we need to consider what you would get as a y value back when you put -2 in. Well, of course, if you put -2 into this, you're going to get -3 right there on the y-axis. Okay, so that point there would correspond to -2, -3, where -2 is the t-coordinate and -3 is the x-coordinate. Okay, so that's that. Now, if we look at the other side of this, where it's obviously it's not drawn brilliantly to scale, but you get the idea. We've got t equals 5, so I'll just put that in here. That will be at the point t equals 5. If we read that off, what we're going to get, well, if we get 5 times 2, which is 10, plus 1, which is 11. Okay, now we've got those values. Because this is an increasing function, x is an increasing function of t, we can see that the range is going to span between -3 and 11. And you can get that directly because by spotting that it's a linear increasing function, you can simply say, well, if my t values are valid between -2 and 5, then by doubling them and adding 1, so I'll just demonstrate this. So doubling and add 1, so double -2 is -4, add 1 is -3. Double and add 1, that's going to give me 11. You can see that the values correspond exactly to what we've just shown on the graph at -3 and 11. Okay, so that's the domain. So we'll just write that more formally now, just to answer the question properly. So the domain is going to be between -3, and these are your x values, remember, because of course 2t plus 1 is equal to x, and 11. Okay, and I might just make that stand out a bit more as well. So that's your domain done. Now we're also asked for the range of f of x. Now the range, I'm just going to do over here, so I don't want to encroach onto the graph that I'm going to draw in the next part. So for the range, this is part B, and it's the range. Again, you've got more space than I have to do this. We can look at equation 2. Now, if we plot equation 2 on a graph, which I'm going to do, it's going to look something like this. So again, this is going to be the t-axis, and this is going to be the y-axis. All right, it's just a sketch. Now, we can see because of the -1 here, that's where its minimum value is. So it's going to be about there. And then we're going from -2 up to 5. So I'm just going to sort of squish this down a bit, and you'll see why in a second. So going from -2 up to 5 is something like that. Right, now it's t² subtract 1, and I've drawn that within the values of -2 and 5. So let's just label everything now. Now, when we put in -2 into this, -2 squared into this, I mean, -2 squared is, of course, 4 subtract 1 is 3. So that's going to give me, I'm just going to make this a little bit longer just so it looks a bit more realistic. So at -2, which is approximately here, this point here is going to return the y value of 3. Okay. Now, obviously the y-intercept is at -1. And if I put in 5, which is over here, and you can see the scale's not particularly good on my drawing, but never mind. We get 5 squared, which is 25, subtract 1, which is 24. Okay, so that's the y value returned when you put t equals 5 in. That will give me a range that we can see clearly now, going from -1 up to and including 24. Now, if you did this naively, you would, if you put in t is -2 and got your 3 back, and then put in t is 5 right here and get your 24 back, you would probably think that the range would just be between 3 and 24. Now, obviously, you'd be wrong in that because there is a minimum value between t is -2 and 5. So you've got to be really, really careful. And another way, if you don't want to sketch the graph, have a look at where the maximum or minimum would occur in this situation. You can see here that because it's essentially t subtract 0 squared subtract 1, if you do it in completed squared form, that the mirror line is obviously at 0, and 0 is right within that domain. So you know that the minimum value will occur between -2 and 5. So you'd be anticipating that the minimum would be actually at -1 and not at -2. Or not at 3, I should say. Okay, so just be aware of that. So let's write down our range now. So this is going to be between -1, as I've just argued, inclusive, of course, up to 24. And it's done, I don't know if it's done to catch you out, but it's definitely done to test your understanding. Okay, so sketching graphs, again, is really, really important. Now, for the next bit, we've stated our domain and range. We now have to sketch the function within the given domain for t. Now, the function itself, y equals f of x, that's what we're going to do now. So we know what the range is. Okay, we've got the domain as well. So we've got a rough idea of what this is going to look like. So let's start sketching. We've got this space here. Again, hopefully you've not used up too much space on yours. So I know the range is going from -1 to 24 in the y direction, and from -3 to 11 in the x direction. So something like this. All right, and then we can label the axes. So we've got the y-axis this time, the origin, and the x-axis. All right, and there's a few things we can deduce from this. We know that there is a minimum, okay? We know where it occurs because we've got our fantastic Cartesian form over here. So we just have to put all that together. So we know the minimum is at -1. We just need to figure out where the minimum occurs. So what we can do now is to find out where the mirror line is. If we set x subtract 1 over 2 equal to 0, okay, that's one way of doing it. We can see that x subtract 1 would equal 0, i.e. that x equals 1. So that's where our mirror line is. So I can indicate that on my graph. So we're going to have a mirror line at 1 and a minimum value at -1. Another thing we can do is just figure out where the y-intercept is. So, excuse me, when x equals 0, we get the y-intercept, don't we? So when x equals 0, we're essentially going to have -1/2 squared, which is a quarter subtract 1, which is of course going to be -3/4. All right, so that gives us our y-intercept. So it's about there, -3/4. Okay, and then that minimum value is at 1, -1. So we've got an idea what it's going to look like. Now, of course, we can also figure out what the x-intercepts are. So just moving on from that. So the x-intercepts, let's see where this graph crosses the x-axis. I'm just going to change the pen color a bit. So the x-intercepts occur when y equals 0. So we just have to set all this equal to 0 like that. Now, to do that, obviously I've got to add 1 and take a square root. So I'm essentially going to get two results. So I'm going to get a result when x minus 1 over 2 is equal to what would essentially be the square root of 1, which is going to be plus or minus 1. Okay, so I've got my two answers. So therefore, x subtract 1 would equal plus or minus 2. And so therefore, x would either equal 2 plus 1, which would equal 3, or x would equal minus 2 plus 1, which is, of course, minus 1. So that gives us some more information. So we have x-intercepts at -1, so that will be about here. It's the mirror image of the mirror line. And at 3, as you'd expect, because the spacing is, of course, 2 on each side. Right, so this is all looking very nice. So the domain, we have to sketch it within the given domain for t, as stated here. Now, the given domain for t corresponds to a given domain for x, which we found out right up in the top right-hand corner. So we've got to go from -3 up to 11. Now, obviously, my scale is pretty bad. So I'm just going to have to squeeze 11 on here. Maybe it's logarithmic, I don't know. And let's draw the curve in. So the minimum point is here. So -3, it's going to come down like this. And it's going to go through, and then it's going to soar up, something like that. It's not the best graph I've ever sketched, but there you go. We actually know what the y value is. That corresponds to that 11. Of course, we found out earlier it would be 24 because the range is from -1 up to 24. So my y values are a lot better than my x values. So that's essentially it. So we've got all the important information on there. We'll just label it y equals f of x. And just to bring it all together, just think about what we've used to sketch this. We've got a lot of information on the board there. We used the mirror line by setting the squared bracket equal to 0. We got the mirror line at x equals 1 because obviously it's a quadratic. We found the y-intercept pretty quickly by setting x equal to 0. We also found the x-intercepts by setting y equal to 0. and we use the domain and range that we deduced in part B, which were here and here. So you can figure out quite a lot in a short space of time. Okay, now in this next example, we're going to do things slightly differently. And there's a bit of a disclaimer just before we begin. It says sometimes it's easier to arrange both equations to give an expression for t, as shown in the next example. Well, yes, it is, but there's also other things that you can do as well, especially when we start looking at trigonometric parametric equations. So in this instance, we've got two parametric equations defined using the parameter t. We've got a domain, excuse me, we've got a range of values of t here, strictly greater than 1, which would avoid any singularities. So let's have a look at this. Now, if we just label this equation 1 and this equation 2, like so, we simply have to make t the subject in both. Okay, so that's what it means by rearranging both equations. So I'm just going to make a note of that and just be aware that this is a viable strategy. So make t the subject. Again, write this down, annotate your notes. Okay, it's really good for revision. Make t the subject in both equations. So we'll focus on equation 1 first and then move on to equation 2. Our goal is to generate a Cartesian equation. All right, and it's not asked to present that Cartesian equation in any particular way. So that's a bonus. Right, so rearranging, I'm going to multiply both sides by t plus 1 first. So we're going to have x multiplied by t plus 1, which is equal to t. Okay, now I need to expand everything. Remember, my target is to make t the subject, so I've got to get all the t stuff on one side. So we're going to have xt plus x is equal to t. So I've got xt and t on different sides. I'm going to subtract t from both sides now. Okay, and I'm going to subtract x from both sides. So there we have it. So we've now got all the t variables on the left-hand side. I can now factor them out. So we have t multiplied by x subtract 1 is equal to negative x. So therefore t is going to be negative x over x subtract 1. That's essentially it. If you don't like having the negative x in the numerator, and part of me doesn't like that for some reason, you can multiply top and bottom by negative 1. It does not change the nature of the fraction at all. And if you do that, you just change the signs of everything. This is an option. You don't have to do this, but so it's going to be x over 1 subtract x, and they're identical statements. There's nothing wrong with that. Now, moving on to equation 2, which I'll just do here. So equation 2, we do the same process. And obviously, if you're not good at rearranging equations, there's some worksheets from the GCSE to A-level transition booklet that you can have a go at on this. Loads of work on rearranging equations. So multiply by t subtract 1 this time. So that removes the denominator. Multiply it out. So yt subtract y is equal to t. Okay, let's get the t variables onto the left-hand side. So I'm going to subtract t from both sides and add y. Okay, now we can factorize the t. Equals y. Okay, and now we can divide by y subtract 1. Okay. So that's that. Nothing wrong with the presentation there. Now notice we've got t, the subject, in both equations. How do we form a Cartesian equation? Well, we set them equal to each other. So Cartesian equation, that's my shorthand for equation. So set both equations equal to each other. Now, if we do that, of course, we just get the Cartesian form straight away. So we have x over 1 subtract x would equal y over y subtract 1. Now, you don't have to make y the subject here. That's a Cartesian form. You're not asked for it in a particular way. So that would be absolutely fine for your answer. Okay, and then if you're asked to do anything else, obviously domain and range, then you can do that separately. Okay, so that concludes example 2. For our final worked example, example 3, we have a parametric equation for x defined using natural logarithms. Okay, y is a reciprocal function of t, and t is strictly greater than 0. Okay, that is really important. I'm going to ask you to really focus on that because it gets forgotten in many situations. So our first job is to find a Cartesian equation of the curve in the form y equals f of x. So we don't have the luxury of just writing it however we like. We have to make y the subject, and we also have to find some constant k, which would also specify what our domain is. Okay, k is a constant to be found, and this is going to be the domain. Well, let's have a look at that first of all. If t is strictly greater than 0, that means that obviously t is a real number, and it puts a restriction on my log function in my x equation. So if we just have a look at that, I'll just write it down. So for a, x is equal to the natural log of t plus 2. And if we think about what that graph would actually look like, we could sketch that. So the natural log, you don't have to do it, but I just recommend this because it's just good practice. It gets you used to curve sketching, gets you more familiar with the functions and transformations. Now recall that the natural log of x, I'm just going to draw that first and I'll erase it. So the natural log of t in this case is an increasing function like that, which passes through 1. Now, because it's t plus 2, that is a translation, which means I have to move it 2 units to the left. Now, if we do that, of course, the origin will be sort of hopped over, and we're now going to have a y-intercept at -1. So for this function, this x function, it's actually going to look something like this. So it's going to cross at -1. I'm just going to, so it's going to look something like that. And it's going to have an asymptote, a vertical asymptote at -2. So x equals -2 more specifically. Okay, and then the y-intercept will be at -1. So that would be x is equal to the natural log of t add 2. Okay, I'll just label this would be x is equal to the natural log of t. So you can see the difference. So it's a translation 2 units to the left. What are the implications of this? Well, notice that we're only allowed to put in t values that are strictly positive. So that has not changed. So I'm only allowed to put in t values along here. So what I really need to do is to figure out what that y-intercept is right here. And that would help me with my range as well. So my y-intercept is, of course, if I put in 0, this must, of course, be the point the natural log of 2. Okay, so that means that my range of x must be strictly greater than the natural log of 2. It's as simple as that, really, because the range in this case, because the x-axis is on the vertical axis, that's my range. Okay, so anything greater than log 2. So in doing just a few steps like that, we can see clearly that x has to be greater than the natural log of 2. That is just a constant. Okay, you can work it out on your calculator as a decimal, but there's nothing wrong with that. That's the exact answer. Now, we haven't actually found the Cartesian form yet. What you'll notice, of course, is that in this instance, equation 2 right here looks a lot easier to deal with than equation 1. So let's start with equation 2. Now, if I make t the subject, I won't write it out again this time because we've said it a couple of times. If I make t the subject, I'm simply going to get t is equal to 1 over y. Okay, and if I sub this into equation 1, what will happen? Well, I will get x is equal to the natural log, and then I replace my t with 1 over y, like so, and then I add 2, and that would seem to be the end of it. But there is a problem. Okay, it is a Cartesian equation. There's nothing wrong with that, but it's not in the form we need. It has to be in the form y equals f of x. So now I have to make y the subject. So make y the subject. So again, rearranging equations is absolutely essential for this. Now, the problem I've got is that my y variable is trapped inside this bracket, which has the log function applied to it. So I've got to somehow release that. How do we undo a log function? Well, we've got to exponentiate both sides using base e. So this is how we do it. So I'm simply going to say e to the power x, that's exponentiating the left-hand side, would be equal to e to the natural log of 1 over y plus 2. All that's in the power. And e to the log of anything is just the anything back. So therefore we get e to the x would be equal to 1 over y add 2. We've now released the y variable. Okay, now I can subtract 2 from both sides. So therefore e to the x subtract 2 would be equal to 1 over y. And then if I just reciprocate both sides, I get my y. There's other ways to do this as well. If you've done it a different way, if you've paused the video and had a go at this, that's really good. And you got it some other way, that's absolutely fine. And there we have our Cartesian equation in the form required. All right, so that was all part A. Now for part B, it says state the range of f of x. So once again, I'm just going to just cordon off this corner. I hope you've got enough room. So for part B, for the range, we can look at the graph of y equals 1 over t, just very briefly. So I'll just do a really simple sketch of that. Put the t-axis there, the y-axis there. Remember, of course, that t is just positive values, so I don't need to worry about the two left-hand quadrants. And 1 over t is simply the reciprocal graph, isn't it? So it's just this, asymptotes vertically and horizontally. So if that's the case, well, the y, the range, I should say, I apologize, is simply going to be anything greater than 0. So let's write that down. So if t is greater than 0, then automatically y is greater than 0. So the range y is greater than 0, and that was just looking at, again, I'll just asterisk this y part, the y equation. Okay, you just need to deal with that. You don't need to worry about the Cartesian form that we just found. That looks a lot more complicated. Okay, it's a bit more complicated in a sense, but just stating that y is greater than 0 will be absolutely fine. Okay, so that concludes the examples. Please try the exercises, and the best of luck.